So I'm Richard from Gizmodo, Japan. We are a tech media. We like these new high-tech things with science and stuff. So awesome vacuum. Who are you?
Very nice to meet you. So I'm James. I'm an engineer for Dyson. Have been for about 5.5 years, and I'm now based in Tokyo to research specifically Japanese homes, Japanese users, and how we develop technology that delights them.
Awesome. Nice to meet you, James.
Nice to meet you.
So my first question would be, so Dyson's vacuums are purely based on, well, not purely, but mostly based on the
Cyclone technology.
So for novice people, what is the difference between Cyclone and like the conventional filter vacuum?
Sure. So it's really the invention of our company. So James Dyson used to use bagged vacuum cleaners, but the problem is as they block up and filter out the dirt, the suction power drops. So he bought a really expensive one, but was really frustrated that he paid that much money and the performance just got so bad so quickly. So he was actually walking past an industrial sawmill, and he saw that they were using this on a massive scale to separate sawdust out of like cutting wood. And so he applied the technology, and he made thousands of prototypes and came up with the very first cyclonic vacuum cleaner. So that was our original design.
This one?
This one, yeah.
Wow, that's pretty big though.
It's huge. So it was in a great big upright machine, but at the time it was a fantastic innovation.
So like, how does it work?
So the air spins around the cyclone, and obviously as it goes further and further down the cyclone, it spins faster and faster. And the faster the speed of the air that it can travel, the centrifugal force just forces the dirt out into the bin. So the air escapes out and the dirt drops down. That's the basic principle.
What I understand is that the air comes in like this, and then it goes out here.
Yeah.
Does it go up here?
So it goes up, and then the dirt drops out the bottom.
Right. So there should be a pipe here, right?
Yeah. So it flows. If you look, so the air's going to come out, the dirt's going to go down. So if I compare it on here, the dirt's going to be ejected into the bin, and the airflow is going to continue upwards towards the motor.
The reason why Dyson's vacuum have really strong suction is because it's cyclone, and it keeps the clogging from happening.
Yeah, so it's kind of a mixture. So by using cyclones, you don't lose the performance over time. So that's really good for a start, because you're not losing your performance. Even to this day, some vacuum cleaners, after several uses, will see a significant drop in their power, because the power is reduced as the airflow's restricted. So you want to do everything you can to filter out the dirt, but everything you can to give the airflow the easiest path through the product. So that's why I was talking, some of these really minute changes just decreases the amount of air pressure in the product, and so you get much more suction.
The suction, it comes from the strength of the motor, I suppose?
Yeah, so the strength of the motor gives you your maximum suction potential, and then there's a whole series of aerodynamics through the machine that limit that potential.
Can we go to that one and talk about it?
Yeah, perfect.
The air and the dust comes through here.
Yep.
And then there's like the first set of...
Yeah, so we have a larger cyclone feature that's in the middle. It's like a great big one, and that's just going to get rid of the big pieces of debris. Think like a piece of cereal or something like this. And then the airflow is going to pass over this metal mesh that has like these tiny chemically etched holes in it. And then, so the 0.5 millimeter debris is then already in your bin. Then the air goes up into the cyclones where it spins, and the debris is separated back into the bin, and the airflow continues where it will pass through this filter where the red sticker is into the motor, and then as it exits it comes out again of this surface, and that's where your purified air comes from.
Cool. So the motor can handle these tiny little particles?
Yeah.
That's fine.
Yeah, so in some systems, if you imagine a hairdryer, it's a very similar process. You've got a great big motor. The bigger the motor, the more kind of debris and rubbish it can handle. So in quite a lot of conventional hairdryers, there's no form of filtration at all. They just let it go straight through the motor. Right. But that's not what we want to do. We want to filter out as much as we can, so the motor's only dealing with tiny microscopic particles in the airflow, and then these will be captured at the post filter.
Could you tell me about the aerodynamics that's going on here? So which part is doing what?
Okay, so this is your motor. So this is just creating something that spins, right? And then this is your impeller. So it's the inverse of a propeller. So on a boat, you have a propeller and it spins and pushes. An impeller spins and sucks. So the movement of those, aerodynamic fins chases the air in through the product and through it, and then it's obviously exited out the back and through the vents.
So this thing spins this way.
Correct. So I think you can see.
Whoa.
But you can see there's resistance. So every time I spin it one time, you have magnetic poles that basically go positive and negative and create the rotation. So every time you see me do it, I'm just pushing it from one magnet to the next. So
Can I try?
Yeah, please.
Wow, that's hard.
Yeah.
These magnets are really strong.
Yeah. So what you're doing in that motor is you're using your circuit board to continuously trigger on and off between these four rotors, and that's what's creating the spin.
So I wanted to ask this. It's already known that Dyson's motors are really strong.
Yeah.
And they're one of the best brushless motors out there. Z brushless motors. What did you change here that's allowing this to be so compact and still powerful?
So I think it comes down to two things really, and I work as a quality engineer, so it's kind of my field. But I think the first thing is material choice. You put really good materials into something, it's going to be more durable, it's going to perform better. Going to arguably be more expensive, but material choice is really important. So as I said, top quality materials in there, particularly the neodymium magnets. So the 4 magnets that you can feel, really high quality source of material. And then it's the precision. So you need to balance that impeller, because any slight inaccuracies in it, 105,000 rotations per minute, you don't want something doing this. So it's all about getting the process control. The plastics need to be very carefully molded. The balancing, so we'll spin it and test it and check its balance, and we'll just do microscopic kind of corrections to it. The filaments, they're winded by a machine in incredible process detail.
What would you say to those people, and what's the biggest appeal point?
I think it's just a beauty of engineering. So it's taking concepts as far as they can. I mean, Dyson doesn't make products unless it feels that they're going to be best in class. So I've been an engineer in the UK where we do some of the really earliest development stuff, and if we feel like we're putting out a product that just isn't the best in class, or arguably the best in class, we just discard the project and keep those lessons learned. So, I think our machines are quite an engineering piece of beauty, and I understand that there might be a barrier price point, but there are different price points within our range, and I think come to the Dyson demo and try it and see if you think it's worth it.
Okay, I think that'll be it. Can you say see ya to the camera? Can we do it together?
Yeah, of course.
3, 2.
See ya.